We are going to start with basics. Okay, so let us talk about first what do you mean by transformer. Now, transformer is basically a device which transfers electrical power from one circuit to another circuit without change in frequency. Now, please remember that it transfers the signal without changing the frequency. The frequency remains the same. The voltage may increase or decrease, or the current may decrease or increase, but then there will be no change in frequency. Fine. Second point is, it is essentially an AC device. Transformer will not work on DC. Fine. Okay. Yes. So basically this is how the transformer looks like. So it has a rectangular core. Okay. That core is made up of soft iron material. Input is applied at the primary coil. Now it has two coils wound on two limbs. Now what do you mean by limb? This portion. This portion is called limb. So in fact even this is limb. Okay, so two pure inductors. Now when I say pure, the condition is ideal condition. Fine. So two inductors are wound, or two coils are wound on two limbs of the transformer. The one wherein we give input is called the primary coil, and the one where we take the output is called the secondary coil. Fine. Okay. Now what happens is, first of all, what do we do is we apply some input signal at the transformer. Now this input signal is represented by Vp, and this is, again, as I said, this has to be an AC signal. Okay, now see, this is a coil and it is wound on one of the limbs of the transformer. Now as soon as the AC flows through this, okay, see, we are applying the voltage. So since the circuit is closed, the current is going to flow, correct? This current is alternating in nature. Now whenever alternating current flows through a coil, immediately flux is generated, isn't it? So this flux is again alternating in nature. Fine. And this flux, or to be precise, magnetic flux, starts traveling. So whatever path it gets, it travels through that path. So the path, this path, see, is shown here. I think I should take some other, yes. So this is the path. Okay. So you can see that some of the flux is passing through the secondary coil also. It means it cuts the coil. Now, as per Faraday's law of electromagnetic induction, a voltage is induced in the secondary coil. Fine. Now, this voltage, as per Lenz's law, will oppose the cause. It means, what is the cause? This flux. And why this flux is getting produced? Because of the input voltage or the applied voltage. So actually I can say that this induced voltage will be in a direction opposite to the primary voltage or input voltage. Fine. The induced voltage will be 180 degree out of phase with the primary voltage. Fine. So now we have induced voltage in the secondary. Now which type of voltage is this? Is it a self-induced voltage or a mutually induced voltage? Now whenever the voltage is induced due to the flux of its own coil, is called self-induced voltage. And if the voltage is getting induced due to the flux produced by some other coil is called mutually induced voltage. Now in this case, the voltage which is induced in the secondary is going to be mutually induced voltage. Fine, okay? Yes. Now if the circuit is closed, because of this induced voltage, the current starts flowing. Fine. Now, if you see, we had applied the signal at the input, but we are getting output also. It means it has transferred the signal from input to output. Now, please remember, it does not change its frequency. The frequency remains the same. Fine. But then, on what factors does this induced voltage depend? So this induced EMF can be given as E is equal to minus N d phi by dt. Now why minus? Because it is in phase opposition, correct? So any induced voltage will be given by E is equal to minus N d phi by dt. Now what is d phi by dt? It is rate of change of magnetic flux. Now what is N? N is going to be the number of turns in that coil, of course. Fine. So if you talk about here, input primary, input or primary or output or secondary, here we will have two induced voltages. See, you have to understand one point, that we are supplying input current, input voltage. But then this flux is alternating flux. So continuously it is changing, and some of the flux is again, traveling and cutting the input or primary winding also. So there will be a voltage which gets induced in the primary also. Okay. So basically here you have two induced voltages. One is primary induced voltage, which is a self-induced EMF, and secondary, the second one is the induced voltage in secondary, which is mutually induced voltage. Fine. So the flux is same, correct? So flux is same, which is phi. But the number of turns in primary and number of turns in the secondary is going to be different. So N1, see, subscript 1 denotes primary and subscript 2 denotes secondary. Fine. So when I say E1, it means the induced primary EMF. It is equal to minus N1. Now what is N1? Number of turns in the primary coil multiplied by d phi by dt. Similarly, E2, induced voltage in the secondary coil. Fine. Which is equal to minus N2, which is the number of turns in the secondary coil multiplied by d phi by dt. Okay. So this is how the voltages are induced. Now let us talk about various symbols. Now here we have two types of transformers. One is called step up transformer and another is called step down transformer. Now if you carefully notice here, the number of turns in the primary is greater. So when I denote it by N1, and if the number of secondary turns is N2, then it is clearly visible then that N1 is greater than N2. Correct? It means that the input voltage is greater than output voltage. It means it is a step down transformer. Now what is the meaning of step down transformer? Where the output voltage is smaller than the input voltage. I can write that VO is smaller than VI, correct? Now for the sake of simplicity, I am avoiding V1, V2, E1, E2. Okay, let us be clear that it is an input voltage and output voltage. So step down transformer is a transformer which has more number of turns in the primary and lesser number of turns in the secondary. In other words, I would say that here the output voltage is smaller than the input voltage. Then what would be a step up transformer? Step up transformer would be, yes, N1 here is smaller than N2, right? Correct? Yes. It means that here VI is smaller than VO, or I can say that VO is greater than VI, correct? So step up, it is stepping up the signal. It means it is increasing the signal, or else in other words I can say that it is a type of transformer wherein output voltage is larger or greater than the input voltage. Fine. So this is the general symbol of transformer. Now you have N1 here, N2 here, and these are the coils in primary or secondary. Correct? And these are the two lines. Now these two lines represent the core. Okay, these two lines represent the core. Now suppose somewhere it has been drawn like this. There is no, there is nothing in between. It means that air acts like a core. So you do not have a material, solid material. You have air in between. So in one way, N1 and N2 might be specified, and even this is symbol of transformer. Now you must be thinking, where do we use this step down transformer and where do we require this step up transformer? Correct. So basically transformers which are used near generating station, means where the signals are getting generated, produced, there what we do is we use step up transformer. Fine. So what do? We have, now suppose we have 11 kV transformer or 12 kV. We have generated 11 kV or 12 kV. So what do is we will step up it to say 10 times, 20 times, and even larger. Fine. Now why do we do that? Because by increasing this level of the voltage, the efficiency of the whole system also increases. And actually why this increases? Because by increasing the voltage, the losses are reduced. So in turn, the efficiency increases. Now, okay, step-up transformers are used near the generating stations. Fine. Now, where do we use step-down transformer? So now see, generation is not enough. Suppose you have generated the voltage, right? But then it has to be distributed again. Where? To our houses. We get 230 volts, 50 hertz supply. Correct. So this is called distribution. Fine. So generated is okay. The signals are generated. But at the time, sorry, sorry. Now at the time of distribution, these signals are stepped down. Okay, because you cannot give such high voltage to household supply. So there at the time of distribution, these voltages are reduced or stepped down to 230 volts. Okay. Now let us go to construction of transformer. So this is how the construction of transformer looks like. Fine. So you can see that core is made up of laminated steel. Correct. Now how laminated steel? It means thin sheets are first used and those are laminated. Now why they are laminated and how they are laminated? Okay. So what is done is very thin sheets are used and it is coated with thin layer of varnish. Now what is this? Why are we doing this? Now when we apply varnish, see, to each single sheet a thin layer of varnish is applied and finally they are stacked together. So the second figure shows you that particular, how this is done. So single sheet is taken and finally they are stacked together. So what is the function? Why do we require this application of varnish? So varnish basically increases the resistance. So what happens after the increase in resistance? The eddy current reduces. Okay, so eddy current losses are also minimized. Fine. Now one more loss is there which is called hysteresis losses, which we have studied in our earlier classes, and we know that hysteresis loss can be reduced by using soft steel material. So here we use very high grade silicon steel. Okay, these are called soft materials. So here the hysteresis losses are less. Fine. So this is how the transformer is made. Now we have types of transformer. Fine. But then this categorization has been done on the basis of the windings. Okay, on the basis of windings. So which type of windings are there in that transformer? Accordingly, categorization has been done. So here we have core type transformer and shell type transformer. So basically this is how they look like. Fine. So in core type transformer, you have the core at the center and then windings are there at the edges, two ends. Right. So windings are there at two limbs of the transformer, or in other words, I can say that in core type of transformer, windings surround the core. It means core is inside and windings are outside. And remember that each winding is properly insulated. Fine. These are all insulated windings. Now sometimes a single winding is taken and which is divided depending on which type of transformer is this. Okay. Something like suppose like these are the windings. Okay. And here it goes like this. Okay. So we can use the single type of winding also, and then it is continued, to the secondary also. Fine. Yes. And the next type comes shell type transformer. Now here you can see that core is at the edge and the winding is wound on the middle limb, center limb. Okay, so here in other words I can say that core surrounds the winding, whereas in core type transformer I would say that windings surround the core, and here I would say that core surrounds the winding. Fine. Now which type of transformer is used where, it all depends on various situations or applications. Okay, yes. So let us compare now both type of transformer. So if you talk about limbs, in core type of transformer we have two limbs and here we have three limbs. Winding position is like here they are wound on side limbs and this is wound on the central limb. Then here the windings surround the core, here the core surrounds the winding, correct? And in core type of transformer you have one magnetic circuit, and here in shell type you have two magnetic circuit. Now how? Now in shell type transformer, see, I'll just show it to you. This is how it looks like, right? So here you have something like this, correct? Yes. So the flux produced travels in this direction. So this is first magnetic circuit, and the same flux, half of this flows through this circuit also, correct? So this is the second magnetic circuit. Fine. So this is how shell type transformer has two magnetic circuits. Now output, core type of transformer has lesser output because it has more losses, and shell type of transformer has less losses and therefore output is more. Now when output is more, efficiency would be more, and where output is less, efficiency is going to be less. Now where do we use core type of transformer? At high voltage applications like power transformers, and shell type of transformers are used for low voltage applications like small electronic circuits. Fine. Now we come to a very important topic called EMF equation of transformer. Now this is very important for our exams. So basically the EMF voltage which is induced in the primary is given by E1 is equal to minus N1 d phi by dt. We have gone through this equation, right? Correct. So basically what is phi? That is magnetic flux. And why magnetic flux is getting produced? Because of the application of alternating signal. So that magnetic flux is also alternating magnetic flux, which can be given by phi is equal to phi m sine omega t. So what we are going to do is we'll be placing the value of phi and then we will differentiate this with respect to t. So my E1 becomes minus N1 d by dt. Instead of phi, I would write phi m sine omega t. So what is the differentiation of sine omega t? It is cos omega t, but again omega t has to be differentiated, right? It is not a single t. It has omega also with it. So we have to again differentiate omega t. Correct? So omega comes. So our differentiation, after differentiation, should I write this? Okay, I'll do that. So d by dt sine omega t. So this is taken as a single variable. So this becomes cos omega t. Again it would be d by dt omega t. So it would be cos omega t, and differentiation of omega t would be omega. Fine. So this is how we get differentiation of sine omega t as omega cos omega t. Okay. Yes. So cos omega t, we have minus sign. So minus cos omega t can be written as sine omega t minus 90. That is pi by 2. Correct? So what we will do is we will replace cos omega t by sine omega t minus pi by 2. Please note that what does this show? E1 is equal to sine omega t minus pi by 2. It means that the self-induced EMF lags the flux by 90 degree. Okay, self-induced EMF lags the flux by 90 degrees. So suppose if I wish to draw the phasor diagram, here is my flux. So this self-induced EMF will lag magnetic flux by 90 degree. Okay, yes. So the maximum value. Now what is the maximum value when sine theta becomes 1? Okay, so maximum value can be given by E1 max. Sine theta becomes 1. Theta is omega t minus pi by 2. So we get N1 omega phi m. We will place the value of omega. What is omega? 2 pi f. So it becomes 2 pi f. Okay. And in AC, we are always interested in RMS value. We never talk about peak value, right? So in order to convert, what is the relationship? What is the relationship between peak and RMS value? RMS value is equal to, we have done this in AC circuit, peak upon root 2. Correct? So RMS value will be peak upon root 2. Yes? Correct. So we will divide, see, E1 max is equal, E1 is equal to E1 max by root 2. Okay. So we will divide this equation 2 by root 2. Okay. So after dividing, we will get root 2 pi f n1 phi m. How did we get that? How did we get that? Just wait for a second. I will just erase it. This is sufficient. Yes. So E1 would be E1 max by root 2, right? So we have 2 pi f n1 phi m upon root 2. So this root 2 gets cancelled by this. So we get root 2 pi f n1 phi m. Fine? Okay. What is the value of pi? 3.14. So we will put that value. And here we got E1 is equal to 4.44 into F into N1 into phi m. Very important equation. Now what factors does this E1 depend on? It depends on frequency, it depends on the number of turns, and it depends on the maximum flux. Now similarly, we can write the equation for E2 also, except for N1 is replaced by N2, otherwise the whole equation is same. So E2 becomes 4.44 N2 into 5M. Okay, so this is the equation for our transformer. This derivation is very important. Fine. And let me tell you one more thing here, that you must have studied a concept called flux density, and we represent flux density by phi, isn't it? And what is the flux density? How is it represented? It is represented by phi upon A. It means how much flux is there in this much area. Okay, what amount of flux is there per unit area. So we can also write that maximum flux density would be the maximum flux upon area, or else this phi m can be written as Bm into A. Okay, so why I'm telling you this equation? Because the same equation can be converted into 4.44 into F into N1 or N2, depending on whether we are talking about primary or secondary, and then we can put the value of phi m, which is Bm into A. Okay, so see, in some numerical, it is quite possible that they have not specified the value of phi m, but they have specified the value of Bn. Then how will we, calculate induced EMF? So by using this equation, we can calculate it. Fine. So I hope this much is clear to you. Yes. So now we shall talk about transformer ratio. So now you have this, again this is very important topic. So you have E1 is equal to this and E2 is equal to this. So what we will do is, we will divide equation 3 by equation 1. Everything will get cancelled except N2 and N1. Okay, so we have E2 upon E1 is equal to N2 upon N1, and this N2 upon N1 is called transformer ratio, which is represented by K. Fine. Okay, this ratio is very important. Now what is E? It is induced EMF. And what is V? It is applied voltage or the output voltage or the voltage drops. So if I neglect that, okay, primary and secondary voltage drops are very less, so I would say that V1 is approximately E1 and similarly V2 is approximately equal to V2. Correct? Yes. So here, yes. So this is correct. V2 by V1. Okay. So E2 by E1 is equal to V2 by V1 equal to K. Similarly, if I say that the losses are very small, then whatever input, is applied, the same is obtained at the output. Okay. So I can say that V1 I1 is equal to V2 I2, or I'll do the cross multiplication and I will get I1 upon I2 is equal to V2 upon V1, which is again K. Okay, so basically what we are doing is we are obtaining various relationships in terms of E1, in terms of I, in terms of V, So again N. So basically transformer ratio can be E2 by E1, or it can be N2 by N1, or it can be V2 by V1, or it can be I1 by I2. All are same. Please remember that all these ratios have the same value, and that value is known as transformer ratio, which is K. Okay, I hope you understood this. We shall meet in the next lecture now. See.